Welcome to Computer Networks. This is lecture 6. Just wanted to share a few things before we get started with today's topics. First of all, homework 3 is due this week. Hopefully you got a chance to look at it. It's not, once you've done a good job with homework 2, it should be relatively straightforward to do homework 3. Not a very heavy week. It's great. And homework 4 actually builds on homework 3. But for those of you who got a chance to look at it, so it shouldn't be too heavy. Homework 5 will be, part of it will be released today, and I will actually do a piecemeal release for the rest of homework 5 because, as I said, that's the exam review basically, except for the small programming oriented part. It's basically what I'm going to ask you to do in homework 5. The programming oriented part is I'll give you a list of 1,000 different websites, and I'll ask you to find out what web servers they use. And in order to do this kind of study, you'll have to automate some of this discovery mechanism. That's the only programming-oriented part, and rest of it will be just little problems related to the topics we've covered in the class. All right. Any questions about homeworks? Yeah.
Which browsers are you going to use to test it with?
Oh, that's yeah. So I guess I'm not going to tell you which one. It'll be one of the standard browsers. So yeah, we're the one who had problem with Firefox. Are you setting content length correctly? You are. Okay. Yeah. Without looking at the details of exactly what's happening, I don't have an answer to that question. So did anybody else test their code with Firefox? What? Oh, you did. Did you have to do anything special for Firefox?
I kind of just talking about it, but it was just, I had 4 header fields, and it was length, type, accept ranges, just bytes, and one more, I can't remember. But it wasn't anything special.
Might have to look at it a little bit more. Any other questions about homework? Who got a chance to look at homework 3? Or sorry, homework 4? Nobody? Not yet? Okay. A little bit. Did it sort of make sense, or?
About how to, that instead of just doing one connection at a time, it needs to be able to open more. Yeah, I don't know how to do it yet.
Yeah, but it sort of makes sense, okay. Yeah. And that homework also has a link to an article that talks about why one might want to have multiple connections and what are the potential problems. All right, I'm going to talk about student presentations during the class. I'm going to invite some of you to do these short presentations about various interesting networking related topics. You'll hear more about it in the next slide. Just wanted to remind you that there are no TA office hours this week, and there will be makeup hours next week. So usually the office hours are, I think, on Tuesdays and Thursdays, 1.5 hours. It'll be 2.5 hours each. And there's a fast HTTP transfer competition. Once you start working on homework 4, you will see a short description of this competition. If you're interested in participating in this, please let me know. The deadline, turns out, was wrong. The deadline will be in several weeks, actually, for this competition. I'll fix that. All right, so student presentations. So the idea is we get one of you to do a little bit of research about some of these topics and present what you found in the class. That's the idea. Great way to increase your participation in the class if you haven't been asking a lot of questions and offering answers to the questions that are asked. So the way this is going to work is we're going to set up discussion related to each of this topic on our discussion site. And the responsibility of the student is to not only synthesize what has been discussed, but also to do additional research if necessary. So sometimes the discussion will pretty much cover everything that we need to know about these topics, right? But if it doesn't, then you do a little bit of research on your own and present your findings. Very interested in hearing, what is the problem that it's trying to solve, the particular technology that we're talking about, how does it work, and most importantly, so this is the thinking part, right? What are the limitations? How to break it? When will it break? So that's the interesting part. I will send you a link to a site that will allow you to sign up for these presentations. And these are the these are the topics that we'll cover in these presentations before the exam. And any questions about this? And by the way, if you've been participating actively, there is no reason for you to present or sign up for these presentations. I expect you to ask questions when these presentations are made in the class, of course. The presentations will be very short, just a few slides, maybe 2 slides, maybe 3 slides, and you'll be allocated about 5 minutes during the lecture to present these topics. And I'll send you a link about 10 o'clock tonight that lets you sign up. And as I said, if you've been participating actively, please don't sign up, because this is an opportunity for others to contribute to the class. Because not all of us knows about these topics, and we'll get to learn about these topics in the class. Any questions? All right. So we're going to talk about 2 different topics. We're going to wrap up our discussion of applications by discussing what I call peer-to-peer networks, and we're going to start our discussion of transport. We talked about a particular type of peer-to-peer networks last time that didn't require that, for example, when we think about Nutella, didn't require a lot of coordination at a central entity. You just flood the request to the whole network, and whichever node has the file that we're looking for, it responds. That's the type of network that we talked about. We also talked about peer-to-peer networks that are slightly different. For example, the ones that have centralized index, right? Napster, for example. And what you get is the address of a client that might have the file that you're looking for. So today we're going to talk about peer-to-peer systems that are a little bit different from what we've talked about so far. They're called structured peer-to-peer systems, and one of those systems is also known as distributed hash table systems, DHTs. Just to briefly summarize what hash tables are, actually let me ask you, who's heard of hash tables so far? Probably you. So what is a anyone? What's a hash table?
It's just you have a hashing function and you give it some you give it some key, and it maps that to an index in the table and gives you back whatever's in the table at that location.
Yeah. So it turns out hash table is a data structure, first of all. It's a table, so it has many slots. Each slot has an index, and the way you compute the index on which you're supposed to store a particular value is by using what is called hash function. Input to the hash function might be something arbitrary, and then the output is an index. It says, for this key, you're going to use this particular slot. And later, if you need to look up what you stored under that name, for example, use the same hash function. It tells you go to slot number 5, and you have your data there. Does that make sense? You've probably all used hash tables in various ways in programming. Distributed hash tables build on that same idea. The difference is we're going to have a bunch of machines, let's say hundreds of machines, and each machine is going to be responsible for a certain part of the key space. For example, slot number, let's say 0 through 5, is going to reside on machine A. Slots 6 through 10 are going to reside on machine B. In order to implement this, in order to actually get this to work, we need to have a way to map the ID or the key to a particular host, because we're now storing some part of the key space on one machine and the remaining part of the key space in another machine, for example. So we need a very reliable way to map this key to a particular machine. Does that make sense? And there are many other challenges when we think about how we might perform this mapping. One simple way to map this is by saying, let's say our key space consists of let's say, English words, we could just say all the words that have initial letter A through, I don't know, H. They're all stored in machine A. We could say that, right? And then rest of the words, they're stored in machine B. What's the problem with that? Copy?
Clumping.
Clumping, yeah, exactly. What else? So let's say your service becomes really popular. And these two machines are no longer able to handle the load. Now we want to add third machine. So what do we do?
You have to redistribute the entire list.
Exactly.
And you have to tell everybody.
Yeah, you might have to tell everybody of the redistribution. Otherwise, they might go to the old, they might use the old mapping, right? Sometimes some of these resources might be heterogeneous. Not all the machines might be the same. How do you come up with this mapping function if the computing resources are heterogeneous? And we're able to imagine a system that had 2 or 3 or a handful of machines, but if we wanted to scale this to thousands of machines, millions of machines, then we probably need to come up with something more sophisticated to do an appropriate distribution of the keys across these machines. So these are some of the challenges that one needs to think about and really address when we design distributed hash tables. So first, let's think about the namespace. Usually, just like regular hash tables that we're familiar with, the namespace is flat. What that means is there is no hierarchy. There you just have a key, it's a random bit. For example, the placement of bits in the name, it doesn't have any meaning. We are familiar with, for example, DNS names. Those are hierarchical. There is some meaning. In terms of, let's say you have a name that says x.y. So the placement of each of those names actually carries some meaning, doesn't it? There's some kind of hierarchy. So these are flat namespace. These are just random bits. And these are distributed. It's like a hash table. You give it a key, it tells you which machine to go to. So it sounds sort of like a hash table, but it's distributed. And these are the two functions in a DHT API, very, very similar to a regular hash table. You have a get and a put. So this is the operation that the nodes participating in a hash table must be able to provide, which is every node in the system needs to know that given a key, what is the host responsible for that particular key, and actually send a message to that node, right? Not every node in the internet, but the nodes that provide this DHT functionality, they need to be able to support that operation. Given a key, how to route a message to the node holding that key. So before we design a DHT, let's spend a moment thinking about this idea of consistent hashing. So the circle that you see on that slide, that's called the namespace. Basically, the keys in this particular system, they can be any number between 0 and 7. For example, when you call a hash function, the output has some constraint. For example, here's the minimum, here's the maximum. So it's a similar idea. And I actually show a function call there. For example, if our key is, we're going to compute the key based on node IP address, we just call the hash, and you get the node ID, which is in that space. There are some differences here compared to the regular hash table we're familiar with. In this particular scheme of hashing, a key is mapped to what is called a successor of k. A key k is mapped to what is called successor of k. And the reason we need this is we might not have a machine that is responsible for that particular key. For example, in this example, our key can be any number between 0 and 7, right, inclusive. But we don't have any machines at key value, for example, 5. So we only have here 3 machines that are implementing distributed hash table. We only have 3 machines, but we need to be able to store any number, any key, 0 through 7. So what happens is you organize logically these machines in the key space, for example, 1, 3, and 0. And whenever we need to find a machine that is responsible for a certain key k, we just store that in the machine that is successor of k. And one simple way to do that is by just saying successor is basically the computer that has k or is responsible for the smallest value larger than k. Does that make sense? For example, let's think about the key 2. What's the machine that's responsible for the key for that particular key if we go by this algorithm? It's 3, right? Because we don't have any machine that's at that particular point in the key space. So we just store that in the successor for that key. So successor of key k is the node that equals to or follows k in that key space. So why do we need to come up with all these techniques if all we want to do is hash certain keys to certain machines? It turns out if we design a hash table using this particular technique, it's really easy to have us remove the nodes from the system or to add nodes to the system. For example, we want to add a node into this network that's implementing DHTs. If we add a node, let's say, with an ID 6, how many keys do we have to redistribute? Let's think about that. Let's think about ID 4, right? Where was the value for that particular key stored earlier? Node 0, right? But now we're going to insert a machine with ID, we said 6. So clearly we need to grab that value from node 0 and store it on this new node. How about 5? We can do the same thing because it is stored on node 0, right? How about 6? Same thing, okay. How about 7? We don't need to do anything. So approximately, if we have k keys and nodes, in average case, with some definition of average, I don't want to get to the technical definition of that. If everything is evenly distributed, each node is responsible for k over n keys. That makes sense. And when a node, for example, joins the network, how many keys change hands? Probably keys proportional to that ratio, actually. If we didn't use consistent hashing, and if we're just using arbitrary hashing function, let's say that return all random numbers, and we're just trying to partition the hash space by saying, first, let's say we just have 2 machines, and we're going to partition the hash space into basically 2 halves. All the values that come out in the top, let's say 0 through 5 goes to this machine, 5 through 10 goes to this other machine. If you actually try to extend the system doing the same kind of thought exercise that we did, you will realize that organizing the key space in that particular way allows us to add or remove the nodes with minimal disruption, minimal exchange of information. And why is that important? Why do we care about transferring keys from one node to another when we insert a node or when a node, for example, dies? Why do we care about that?
So if you're making a peer-to-peer probably joining and leaving constantly.
Yeah. But what's the problem of coming up with a scheme that requires a lot of key exchange when a node joins or when a node dies?
The rest of the nodes don't know about it.
Yeah.
You have to update all that.
Yeah, so you might actually spend a lot of effort. You might send a lot of messages in the network saying, okay, this node died, so we need to reorganize the keys. Oh, this new node came in, now we need to reorganize the keys, so on and so forth. So here are a set of other examples for the same idea. But this should be sort of obvious to you now, after having gone through that discussion. For example, we have node 8. What is that? What is node 8 responsible for? All the keys that are 5 through 8, for example, in this particular example, right? Let's actually go through this example that shows how we look up the keys if we organized our machines in this particular manner. Remember, one of the properties we said that we should have in the system is each node should be able to route the packet to the node that's responsible for that particular key, right? Otherwise, we have no idea where to store these keys or where to look them up. So let's say node 4 gets a request from the wider internet saying, I want to read the value corresponding to key number 37. So what should node 4 do? You should have some idea for where to send this packet because node 4 clearly does not have that value, right? So it turns out each node maintains its successor. It knows, what is the successor node to it, and that is how they maintain that ring. So what that means is 4 knows that there is node 8 that's in that direction in the key space, right? So node 4 looks at its database, doesn't have key number 37, so it's actually going to send a request to node 8. So what is node 8 going to do? Yeah, it's going to send it to 15 because it doesn't have it. And what happens at this point? We're trying to look up 37. Does this node 35 have the key or no?
No, but it can point to 44 still.
Yeah, exactly. So it knows that it doesn't have the key. And once you found the key, remember this request is coming from the wider internet, and it's only node 4 that is aware of it, right? The request is coming in from the wider internet to node 4, and node 4 is routing this query internally in the distributed hash table. So the response has to go back to 4. Why is that? Because we need to send the reply. Yeah. How do we join a node? This is just a concrete example of what we've already discussed. So let's say we want to have a node with ID 50 join the network. So it's just going to send a request to some arbitrary node in the network. That's the bootstrapping process, right? For example, you probably need a static IP address or some well-known anycast IP or something like that. But this node doesn't know exactly where it belongs in the key yet. So it just sends that request to one of the nodes in the network saying, I want to join this network with ID 50. So what does node 15 do? Because 50 thinks that this node belongs nowhere near it in the key space. So it needs to forward the request to the right place so that you can break the chain, put this node in, and then rebuild the chain, right? So 15 is going to forward the request, so on and so forth. Finally gets to 44. And what does node 44 do at this point? So what does 44 realize? Okay, so there is a node that wants to join the network with ID 50, right? But node 44 also knows what its current successor is, doesn't it? What's the current successor? So what should we do? We should probably put that node in. So certain different types of messages are exchanged just around these nodes. The details aren't too important here. And this node will contact the node that is successor and tell it that this is a new node joining the network. You need to fetch the keys that it will be responsible for, right? For example, key number 45, where was it stored earlier? On node 58. So you need to get those keys. And if you have a predecessor link, you need to get that node to also update that link. And finally, this node will be in the network. You can look at the slides on your own. So what does this remind you? What is going on here? What does this remind you? You've done something similar for at least one type of data structure. Linked list. Yeah. It's a similar idea. And first you need to find out, okay, where to actually put this node. And once you've found where to put the node, you need to fix the links. And you're doing the same kind of thing here. But you're doing this across the network. So I want you to get two key ideas from this discussion, basically. One is, why do you want to organize the hash space or key space in this particular structure? What is the advantage? Why do you ever want to do that? And the answer is, it has some nice properties that become very important when we have a lot of churn in the network, right? If we didn't organize the key space in this particular manner, we could, for example, have this consequence, which is, let's say, node 50, let's say it knows that it's going to die soon. You might actually have to redistribute the key to all the nodes in the networks when we consolidate, if there is no structure like this. Or when there's no structure that enables you to add or remove a node with minimal disruption, right? For example, let's think about the scenario earlier when we said, how do we go from 2 nodes to 3 nodes? Let me just give you another number that will make the point even more obvious. Let's say we have 10 nodes, and we want to insert one more node, 11th node. So how do we redistribute the keys here? Let's say we're trying to balance things. You might have to grab a small fraction from each of these 10 nodes and assign the aggregate fraction to this 11th node. Sounds like a lot more work than this. What if we want to go from 11 nodes to 10 nodes? We might have to do similarly large number of message transfers across the nodes. And we don't want to do that because network is a limited resource, right? We don't have unlimited capacity to transfer messages back and forth. So what we've done so far is looked at various network applications. We've looked at centralized and peer-to-peer architectures, and some homework and also some exercises during the lecture. We've thought about how to design and write network applications, right? Designed several. And we've looked at a few concrete case studies so far. All these applications need a reliable way to send and receive information, right? For example, when we're thinking about HTTP client, we assume that we open a socket, we say get, and we assume that it actually gets to the server reliably. That's what we've been assuming. So next, what we're going to do is think about how the network actually provides this functionality, which is a reliable way to send and receive message across the nodes. And it's the transport layer that provides this service, reliable message delivery service. And that's what we're going to talk about next in this class. Before we get there, I think this is a good time to just take a quick break, and we'll continue in a couple minutes. Any feedback for the class or anything like that?
Are grades going to be posted for the homework posted in black?
Yeah, all the homework grades will be in black. But TA is out of town this week.
Yeah.
But you already have homework 1 grade, right? Oh, so here's one request I want to make to whoever wants to contribute. Could you write instruction on how to resubmit homework? Because it turns out it's not very obvious because Blackboard has some quirks.
You have to take it back and then...
Yeah, you need to do all kinds of things.
Top, it's like a tiny icon in the top right corner.
There's a drop down and you take it back. And
Yeah, could one of you, whoever wants to do this, write clear instruction on how to do that? Because what happens is I get emails saying, okay, I wanted to change this, but I can't, so here's the... And if it's just one person, it's okay. If it's more, then it becomes difficult for me to keep track of, okay, did this person actually figure out how to do this, and did the Blackboard updated that, or should I look at the email version or Blackboard version? It becomes confusing. So, see if one of you could write instruction. That's what that would write.
Super focused. Just like drew everything on the board. Try to figure out like how the tables are kind of like what years and they go to your list or there.
All right, maybe we should get started. So we're going to talk about transport layer, and if you go back and think about the protocol stack, you'll realize that somewhere in the middle it's below the applications, and some of the applications that we talked about in the class, actually there's only one in this diagram, which is HTTP, right? That's the application layer protocol. So the question is, how does HTTP, why is it okay for HTTP to assume that these messages are going to go to the server and come back reliably? And the reason why it's okay for HTTP to assume that is because it's using some transport protocol, and that happens to be TCP in your example, in your homework. You could use another one called UDP, and the result would not be guaranteed. So the transport protocols sit on top of the network layer and provide application-level multiplexing. We'll talk about that. That's an important functionality, and also error detection and reliability. We're going to mostly focus on error detection and reliability, but before we get there, let's spend a minute talking about multiplexing. If you think about what's happening on Bayou, which is where you do most of your software testing, right? Can you imagine how many students are launching the web server at the same time? Or the clients, right? HTTP client, a lot of students. How does the system know which packet to send to which student process? So there has to be some multiplexing functionality, right? The system has to know that. Even if you think about your personal machine, You might have multiple browsers or multiple applications. They're all using the same internet connection. How does the system know which packet belongs to which application? Any ideas? It might be done through ports. Remember, we assigned you a port on which you're supposed to do your experiments. Can you imagine why we did that? Because we don't want packets that are supposed to be for other applications come to your applications and confuse your application. So this functionality is called multiplexing, and the counterpart would be demultiplexing. And the idea is you identify the packets that are going from network layer to transport layer, or transport layer to the application layer, using these identifiers. And port is a well-known way to do that. It's a pretty standard way to do that. We said web server runs on port 80. Why is that important? Because it turns out we configure our web servers in a way that allows them to listen to packets only coming to port 80. For example, we don't want SSH traffic to go to the web server, do we? No. It's the same idea there. Because we want only packets of certain type, or packets that are designated for some applications to reach those applications and not other applications or other protocols. So you need this type of mechanism when you go from, let's say, network to the transport layer. For example, there we saw two different transport protocols, right? TCP and UDP. You need a similar mechanism. It might not be called port, depending on the system that you're looking at, but you need a similar mechanism. And when you go from transport layer to the applications, for example, there is FTP and HTTP on top of TCP. Right? TCP needs to decide when it receives a packet which of those two systems should get that packet. The textbook has a whole chapter related to this, or you can read more about this on Wikipedia or Google. But that's the idea behind multiple. Any questions? Because we're going to move into the error detection and reliability next. All right. So let's think about error detection, because we said transport protocols ensure that messages are delivered reliably to the applications across the network. So one of the things that you need to be able to do if you want to provide that kind of reliable service is you need to be able to detect whenever there is an error. If you have no idea if there is an error, then you cannot say that you have a mechanism that can deliver information reliably. So you need to be able to detect the errors. Typically, errors are detected by adding some type of redundant information to the packet. This information gives you an idea for what the packet is supposed to look like, or what property this packet should satisfy. And here are three standard techniques called Parity, Internet Checksum, and CRC. Have you heard of Parity before? Probably have in computer architecture course or computer organization. What is Parity? Anyone? Because you heard of a parity in a completely different context. What is parity? Have you heard of parity bit in memory? What is it? Because even in that context, there is this particular mechanism is being used to see if there has been an error or not. For example, when you store some information in memory, there could be error in the memory that could flip the bit, and we need to be able to detect that, right? So let's imagine we have that data, 11011101, and we want to provide a bit that would tell us if one of those bits has flipped. If you're using even parity, the property that needs to be true if there has been no error is the sum of all the ones, including the parity bit, has to be even. So how many bits do we have in the data? 5, right? How many ones do we have in the data? 5. So that means if you're using even parity system, we need to put a 1 there so that the total number of 1s is going to be even. Now what happens if, oh, okay, so now once we've added that parity bit, and if you're talking about a networking context, so that is what we'll transmit. The data followed by the parity bit. In computer architecture context, what you probably heard about is we're going to allocate 1 bit as parity bit, and we're going to store we're going to use the rest of the bits on that register, for example, to store the information that we want to store. It's a similar idea here. In networking, we will say in this 8 bits that we're allowed to transmit at a given time, 7 of those bits is going to be the actual information, and then this 1 bit is going to be the parity bit. Let's say there is an error. One of the bits gets flipped. What happens, and how do we detect that? Can we detect that? If one of the bits gets flipped.
Yeah.
Yeah.
Because then the parity bit should be 0.
Yeah. Yeah. So let's say, so whenever we're analyzing these error detection techniques, usually we think about errors either in the data or in this redundant information. For example, here we're talking about parity bit, right? What if that information itself gets flipped? So let's think about what happens if the data that we wanted to transmit, if that gets flipped. Can the parity bit detect that? Yes, right? If one of those bits gets flipped, then we're going to have an odd number of 1s we have to get over. What if the parity bit gets flipped?
It shows up as a pattern.
Right. Because we're going to have an odd number of 1s again. So here's an example of how we can detect errors. Remember, we're trying to detect errors because we might have to retransmit if a message is corrupted.
What if 2 bits get flipped?
So what will happen? Yes.
It won't work.
It won't work. We won't know, right, if it is an error or not. So that's a problem. Let's think about 2D parity. This is just another scheme. You can read about it online. I'm not sure if the book has this. But the idea is you compute parity in 2 different ways. One across the row, one across the column. And you send that parity information along with the message that you're trying to send. Why is this better than, for example, the odd or even parity that we saw in the previous slide? Is this necessarily better? So earlier, when a bit got flipped, all we know is the total number of 1s. It's odd now. So that means some bit got flipped somewhere. We have no idea. How about here? Let's say just this one particular bit gets flipped. Yeah, so we will know that we can actually correct that error. Does that make sense? Because we know exactly which bit got flipped. For example, what will be the parity bit on the 3rd row if that particular bit got flipped? The parity bit is still 1 because that is what we transmitted, right? But it doesn't check, does it? So we know something bad happened on that row because we'll have that parity bit being 1. It just doesn't make sense. So there is something wrong that happened on the 3rd row. How about on the parity byte? We'll be able to detect that something happened on the 4th column. So we know something happened on the 4th column, and we know something happened on the 3rd row. With that information, we know exactly which bit got flipped. So what should be the next step? 3D parity? So the trend that you will notice here is if you just want to detect minimal errors, you can get by with very little redundant information, very little extra information in the packet. If you want to detect more complex errors, you might have to send more information. And if you want to be able to not just detect but also correct the errors, you might have to send even more information. So that's the general trend that we can appreciate in how we design error detecting and error correcting codes. Here's another idea. It's called checksum. Who has heard of checksum? What is a checksum?
Checksum.
How is this different from parity bit? Why don't we just use a parity bit? This basically gives us more granularity. Of course, we're using more information, right? So here's a checksum algorithm that is used by IP as well as UDP. Basically do one's complement sum. And once you computed the sum, finally you do one's complement of that. So are these phrases familiar to you from computer architecture or computer organization? Yeah. Okay. And you transmit data plus checksum. Why do you need to transmit checksum? Because it allows the receiver to check if the data has been corrupted, because the receiver is going to use the same algorithm to compute the checksum and it has to match, right? And how do we define match in this particular case? Because the receiver knows which algorithm we've used, right? It turns out you can use that shortcut. And at the bottom, I provided a link that's a very nice and very accessible description of checksum algorithm, basically. I encourage you to go and read that. It's a very nice description. So how well does it work? In order to answer that question, you have to think about what is the probability that a 1-bit error is not detected. Again, if you go look at that document, it talks about this in a very accessible manner. I encourage you to do that. Does it catch any 1-bit error? This checksum algorithm that we talked about? Because remember, we're doing one's complement sum, right? It actually does. But does it catch any 2-bit error? Here's an example where it doesn't work. Because we're essentially computing the sum. And what that means is, let's say we have 2 words, and if we increment one and if we decrement the other one, the sum is going to be the same. So some of these correlated errors might not be detected by this type of algorithm.
Can this do the error correction? Like 2-bit parity?
Can we do error correction? Yes, you can, but to a very limited extent. If you want error correction, then there's a completely different type of codes out there that you have to use. These are just used for error detection. Then there is CRC. Again, we won't spend a lot of time here in the lecture, but if you want to learn more about it, go to that link. What's one of the limitations of checksum? Because it's important to think about that before we think about even more sophisticated techniques. When it comes to multiple bit errors, just doesn't work very well, and if the width of the checksum is pretty limited, then we're going to miss a lot of errors. So these techniques will let you even decide which bit might be flipped, even with the same number of bits that you're using at checksum. And it uses modular arithmetic to accomplish that. You can go look at it for more detail. So these are the 3 common techniques, and there are many more, to detect if a packet has been corrupted in transit. And that's the only reason we're surveying these techniques, right? So let's say a packet, we detect that a packet has been corrupted. And let's say we don't have the ability, depending on exactly which code we are using, we don't have the ability to correct that error. What do? Yeah, that's the question we want to answer next. Because discarding bad packet is not going to make the transmission reliable. Right? We prevent applications from receiving bad packets. That's important, but they might not receive the data that the sender wanted to send in the first place. So there are different types of reliability semantics that we need to think about, depending on exactly what we're trying to do. One might be one type of semantics is what we're looking for, not the other one. So one semantics is basically we want to make sure the receiver receives the data at least once. That's one type of semantics, right? At least once. For example, the sender sent 5 packets. We want the receiver to receive all 5 packets at least once. There's another semantics called at most once. That's a little bit different. Why might you want one or the other? Is there any point to this? Why might you want at least once versus at most once?
For streaming video, you don't want to keep on resending it.
Exactly. Maybe it's at most once semantics that's useful in that particular case. Does that make sense to people? How about at least once? Why do we want to have at least once? First of all, the application clearly cares about all the packets, right? That's why it's at least once. But why is it not exactly once and at least once?
File download.
Mm-hmm.
That way you can stop it manually if you keep getting corrupted.
Mm-hmm. Yeah, so it turns out when we think about how to implement these reliability mechanisms, sometimes it's easier for the network to send a lot of copies, for example, rather than keep track of, okay, did the receiver receive this particular packet or not? So sometimes it turns out that's easier, and that's the reason why that particular semantics might be desired sometimes, at most, at least once. Does that make sense to people? Because if you want to have exactly one semantics, we need to keep track of the exact packets that the receiver has received, the receiver has not received. But let's say we know that the link is not perfectly reliable, then the easiest way to ensure at least once might be to just send duplicate packets, send every packet twice. We didn't have to keep track of it, and what is the receiver receiving currently, what the receiver has not received. And it might be the case that the receiver is going to receive 2 packets of each ID. But that's fine, because the reason we designed this reliability mechanism is to avoid the overhead of having to coordinate the packet IDs between the sender and the receiver. So in certain scenarios, at least once might be what we're looking for. In certain other scenarios, at most once is what we might be looking for. There's another reason why we might want at most once, and that's because of the way we write applications, we design applications. For example, you designed an HTTP client, right? Would your HTTP client work on a transport that provides at least once delivery guarantee? It's probably not going to work. Why not?
My program was always writing what it received, so it would write the same data twice and corrupt it.
Yeah, exactly. Now your application would have to keep track of what did I receive, what did I not receive, uniqueness of data, and so on and so forth. How about, would it work if it was an at most once semantics? Probably wouldn't work. It's HTTP client, right? All right. So how does the sender know that the packet arrived at least once? Because our goal is to make sure that the packets get to the receiver, reliably at least once. And that mechanism called acknowledgement is basically the receiver telling the sender, okay, I've received A and B. And the sender also sent C, but the acknowledgement has not been received, so that's called timeout. So there is a certain amount of time the sender is going to wait to receive an acknowledgement, and if the acknowledgement is not received, what can we assume in that case? What failed? But there are two, right? One is the message delivery going forward, another is acknowledgement. Which one failed? Sender to the receiver? Not the acknowledgement from the receiver to the sender? Yeah, we don't know actually. Just based on the information that I did, we don't know which one actually failed, right? So this series of diagrams, they explore these possibilities. So we've already seen these kind of diagrams before, right? So we know how to read them, right? The time goes from top to bottom, and that's the reason why the lines are slanted. They're not horizontal, right? Let's look at the first diagram, A. This is the normal scenario. You send a frame, and you receive an acknowledgement before the timeout. Timeout is basically how long you're going to wait to receive an acknowledgement. Scenario B is down here. You send a frame and you did not receive an acknowledgement. It's the frame that got dropped. Because if the frame gets dropped, then the receiver is not going to send any message back, so you're going to have a timeout, right? And the sender is going to send the frame again and you receive an ACK. How about case C? What happened in case C?
Acknowledgement never made it back.
Yeah. You still have timeout. The acknowledgement never made it back, so you have to retransmit. So what happened at the receiver? Is this an at least once semantics or at most once semantics?
At least.
Somebody said at most. No? No. It's at least once. So what happens if you write HTTP client on top of a transport that works like what we see on figure C? It's the transport that has to do the work of making sure that you send a message exactly once to its clients, for example, HTTP client. Because we don't want the application to handle this, because we didn't write the application to handle that, right? So the transport protocol actually does that for you. It will receive 2 copies of the message, and when it receives the second copy, it will say, I've already received this particular message. It's not going to send it to your client. How about the fourth diagram? What happened in that particular case?
The acknowledgement took too long to get there, so it sent another.
Yeah. So is this at most once, at least once, exactly once at the transport? Not above transport, but at the transport. So this is also at least once. We actually end up sending 2 copies. So at the transport layer, if we wanted to ensure at most once, what would we do? We just transmit just once. And let's say the receiver receives 0 packets. Do we still maintain that property? At most once property? Yes.
If it's at the transport layer, yeah.
Yeah. Right? Because we're receiving at most once. All right. So these protocols are called stop and wait protocols. And the reason why we call them is sort of obvious. We transmit, we stop, and then we wait for an acknowledgement. And here are some problems. And we discussed some of this in the earlier diagrams. The data can be duplicate. The acts might be duplicated. But let's think about these 2 other problems. First, we can't fill the pipe. That's a big problem, right? What does that mean? Can't fill the pipe. So pipe here being the network connection between 2 applications. because the sender is going to wait to receive an acknowledgement and not use the incredible network capacity that you might have between these two nodes. And let's imagine these two nodes are separated like large distances and very low capacity lengths. So this network is going to remain underutilized most of the time because the sender transmits a packet and it waits until it receives an acknowledgement, right? A lot of inefficiency. And the fourth problem is it's hard to set the timeout value. Why is it hard to set the timeout value? Yeah. It's just hard to tell what is the right number. On a good day, maybe a small number is the right number. On a bad day, maybe a large number is the right number. And these numbers change. And we need to be able to change these numbers dynamically if we want to be efficient. Right? For example, on a day when we have a lot of network congestion, maybe we want to increase the timeout value. Because using a short timeout value is actually going to make the condition worse. How is that? Let's say we have a day on which there is a lot of network congestion, and we say, and our packets are getting dropped, so we want to be able to retransmit faster so that our receiver can receive the packet. That's actually a bad idea. Why is that?
Because the acts are going to take longer to come back. There's a lot of congestion.
Yeah, and
so
when
if
right,
timeout too slow, you'll miss acts that are coming back.
Yeah. But let's say the links are unreliable and a lot of our packets are getting dropped. If we want to utilize the network properly, we want to reduce the timeout value, don't we? But that's a bad idea. Why is that in this particular case? Because if we reduce the timeout value, we're going to retransmit quicker, and the receiver is going to receive it.
Doesn't that bring down the network even more?
Yeah.
Duplicate all that data, duplicate over and over and over and over.
Yeah, think about what others might be doing as well. And if everyone is doing a very aggressive retransmission with short timeout values, then it's just going to make the network worse and worse. So I hope you appreciate that problem. And that's actually goes to the core of the transport challenge. It's not clear how aggressive you should be. Not just when you are retransmitting, that's what we're talking about here. Goes back to the third point, which is can't fill the pipe. One way to try to fill that pipe is by sending more and more packets, but the question is, how aggressive should you be? And we're going to discuss that in great detail starting next lecture. So let's think about the at most once semantics. So we still need to avoid the duplicates, right? When we write our web client, we actually write to the file whatever we receive. That means we should receive the packets only at most once. It's actually exactly once. How do we ensure that? Because we're going to receive the same packet multiple times. So a standard technique that we use is putting a packet ID into the packet and only providing unique packets identified by that particular packet ID to the application. And if we're talking about stop and wait protocol, it's actually enough to just add one bit to the header, it turns out. Can you think of why? Why is it enough to, generally when it's a sequence number, but if we're talking about a specific case of stop and wait protocol, the simple one that we talked about, it's adequate to just put one bit in the header to avoid duplicates.
You just flag each packet as even or odd, and you transmit the next packet until you know the previous one.
Yeah, exactly. So you just said the first frame that you transmit, you just say this is frame 0, and then you wait until the acknowledgement is received. Let's say the acknowledgement was not received. Right? The sender did not receive an acknowledgement. What do we do in that case? We retransmit frame 0. It is possible the receiver has already received it, in which case, how can it avoid the duplicate? Look at 0, right? Saying, okay, the last frame that I received was 0, and this one, the second one that I received, is also 0. In the next frame that you transmit is frame 1. You can use the same technique to avoid the duplicates. So we've solved one of the problems, right, which is how to avoid the duplicates. The second problem that is very important and becoming more and more important every day is how to fill the pipe. Why is it becoming more and more important every day? It has to do with certain trends and certain types of technology. What is that? And that has to do with it.
Everything is being done over the internet nowadays.
Yeah. And also, what's happening to the links that connect us to the internet?
They're getting bigger.
They're getting bigger and bigger, and if we're waiting a long time to receive an ACK, we're not fully utilizing what we have, right? Even if you think about, let's say, a movie download, let's say you didn't receive an ACK for a particular packet, maybe you should move on and try to get what you can, and then also try to fetch what you could not later. So these are called sliding window protocol, which is rather than transmit one packet and wait for that ACK, you try to pipeline the packet transmission. So the idea is pretty simple. You just say, I'm going to send this many packets at most at a given time or a given period. We call that a window. So let's say our window size is 3. We're going to talk about how to determine the window size. Again, that's a very difficult problem. What's the right window size, right? But let's say we've settled on a window size of 3. We just send these packets back to back because we don't need to wait for an ACK. And once the number of outstanding packets is the same as our window size, we better wait for an ACK. So here, once we've transmitted 3 packets, and before we receive the first ACK, what's the number of outstanding packets? 3, right? So we need to wait for an ACK. And then once we receive those ACKs, we can transmit new packets. So how does this particular extension to the stop and wait protocol solve the problem of underutilizing the links? How does it solve that problem?
You're not waiting for each acknowledgement.
Yeah.
Regardless if it comes in.
Yep.
Still sending out the next data.
Yeah, exactly. Right. What do we need to do to ensure that the transport can correctly identify the duplicates so that we don't inundate the applications with duplicates? Because even when we have a protocol like this, there is a potential for a lot of duplicates. It's the same as stop and wait, right? But we don't want to send all these duplicates to the applications of transport. How do we? So does the earlier scheme work? When we had a bit earlier to identify duplicates, does that work or no? Why does it not work?
Because you've got more than just 0 and 1.
Yeah. So how do we extend that?
Use a longer string.
Yeah. We need a larger counter, right? Okay. So now, those of you who are finding this too elementary, well, some of you have seen something like this before, right? So here's a difficult question. What's the right window size to use? Any ideas? First, let's think about the consequences of using a window that is too large and too small. So what's the consequence? What's bad about using a window that's too large? Okay, let's think about too small. That's the easier case. What's the consequence?
We don't use as much the pipe as we could.
Yeah, right? For example, let's say we make the window size really small. Let's say a window size of 1, then it becomes the standard stop and wait, and we're not utilizing it fully. And even if you make it 2, let's say, you only have 2 outstanding packets at a time, probably not utilizing the link fully. So we understand the consequences for using a window that is too small. How about using a window that's too large?
Increase the potential for the packet loss and then the multiple sends.
Yeah. So using a window that is too large is going to increase the potential for packet loss. Because we might send too many packets, more than what the link can handle. We're talking about sending these packets across the internet, right? So even though the link that we have that connects, for example, my laptop to my ISP, that link might be able to accommodate a window size of, let's say, 500 outstanding packets at a time, but we don't know what links are available beyond that, right? So some of those links could have bottlenecks, and if we try to send too many packets at the same time, that's going to just cause network congestion. Do people agree with that explanation, or no? Sending a window too large. Then how do we determine the right window size?
Carefully.
Dynamic.
Carefully and dynamically, both are right answers. We need to be very careful. Can you give me a traffic analogy in everyday life, from driving, let's say, about how we control the number of cars on the road, because that is what it comes down to, right? Because some of the freeway entrances, they have these meters that control how many cars can go in. Let's say you want to design an algorithm. Because what's your goal? Your goal is to utilize the highways most efficiently. And how do you define what is the most efficient use of the highway? Probably number of cars that can move across a line, probably, if you draw a line across the highway, right? That's probably how you define it. So how would you design an algorithm with the right, for metering, so that you utilize the highway most efficiently? How do you design that algorithm?
Based it on statistics.
But, how so? That's a pretty vague answer.
I mean, you'd want to gather information about at what times can you increase the windows, like in the example, at what time can you increase the rate of change of cars going onto the highway, and when you need to slow them down.
Yeah.
But you don't know any of that. If you don't have any of that data already, you're just kind of guessing.
Yeah. So first of all, you don't want to guess, right? It's clear, right? But I want to hear a little bit more concrete about, okay, what kind of information would you want?
Well, if you can track how many cars are moving at any time, you could see if it's, if they're not moving like fast enough, like you need like 50 cars an hour passing this line, then you can slow down the amount of people that are getting on the freeway, so that way there'll be less traffic and they can move faster.
Yeah, but this problem becomes complicated because, first of all, it takes some time for the feedback to travel. Let's say at a given time you send too many cars. It takes a little bit of time. There's a little bit of lag between the entrance of the car and the congestion build-up, right? That's one dimension. Another dimension is this is happening in a distributed fashion. There are other entrance and exit ramps too, so that actually complicates the problem. We actually face similar issues when we were thinking about what is the right window size in the internet, because we're controlling the amount of information that we're pumping into the network, right? So hopefully this gives you a feel for what we might study in the next few lectures. But before we wrap this up, let's actually describe what we just discussed using diagrams. For example, how might you design the algorithm at the center, first of all, if we're using these sliding window protocols? First of all, you need to know what your window size is. We just said, we actually don't know how to find the right size, but let's imagine, by some magic, we know what the right window size is. So we need that. And we need to know the last packet that was acknowledged, right? And then the last frame that we have sent. Why do we need to keep track of these two pieces of information? Because that tells us, what is the number of outstanding packets, basically. That's a guess for how many packets might already be in the network, right? So, and that's exactly equal or less than the window size. The packets that we've already sent and the packets that are not acknowledged yet. And that's the invariant that we want to maintain. Why do we want to maintain this invariant? But that was the whole point of using the window size to limit the number of packets that we're sending to the network at a given time, right? When we receive an ACK, what are we allowed to do? We're allowed to advance the last acknowledgement received, and that gives us an opportunity to send one packet. How about at the receiver? There is a window there as well, right? Why do we need a window at the receiver? This window does not have to be the same as the center window, by the way. The rest of the stuff on the slide is obvious, but let's think about why the receiver window has to be different, or why it can be different. Because the rest of the stuff is pretty straightforward because there's a similar invariant, right? Can you think of a scenario when you might want to use a different receiver window? So we're talking about transport protocol, right? What uses transport protocol? What uses transport protocol?
HTTP.
For example, right? So if there is a receiver window, does that suggest that maybe there is some limitation of this HTTP client that the transport is trying to be cognizant of? Might be. Perhaps the application has an ability to receive so many packets per second, and no more than that. Perhaps the receiving node has only so much memory. Does that make sense? For example, the sender window is 1,000 packets, but the receiving host can only store 10 packets at a time. Or the application that's running on transport that's supposed to process this packet has a limited ability to process the packets. Those are the two potential reasons why you might sometimes have receive window size different than sender window size. Can you guess an example scenario when the receive window size might be much larger than the sender window size? It's basically the opposite of what we talked about. Let's say we have application that is very data hungry. It's able to process a lot of data, right? A lot of memory. But there's another interesting relation between these two windows. Sender window is typically limited by how much packets you want to inject into the network, right? That gives us an idea for what is the capacity of the network, how much information can the network move from one point to another. Receiver window tells us a slightly different story, which is how many packets can the receiver process, or the application can process at a given time. So ideally, what do we want? We want the network to be able to ship as many packets the application can process per second, right? But let's say, so now having discussed this, let's say we have very powerful machines at the end, but the network is not well provisioned, in which case, what is a likely relation between these two windows? If the network is not well provisioned.
The receiving window is going to be a lot bigger.
Right, right. And let's say we're running really slow programs, at the receiver, and the network is well provisioned, then the receiver window is going to be a lot less. Now, finally, why do we even want these windows at the receiver? And the answer is, we need to keep track of what packet was received, what packet we received, and which packet we have sent it to the application. We need to keep track of that. Why is that? Because this is about reliable transfer. If we don't keep track of this, we will forget what packet we have transmitted to the application on our end. And if we forget that, then we might not be able to guarantee the reliable delivery that we wanted to guarantee. So this has been a very abstract tour of some of the functionality that the transport layer provides. Next lecture, we're going to look at UDP and TCP, which are widely used transport protocols. And we're going to use some of the principles that we talked about, which is how to detect errors and how to make sure that the packets that are lost are retransmitted. And the other consideration is how quickly are you allowed to send these packets across the network. Thank you.